sum of half convention. Okay? So this is something that you get by the radial quantization map. You can just take it for granted. So I'll just give you an intuition of where does it come from, some intuition. So I assume that you know what radial quantization is. The only subtlety is why is there this funny exponent, which is slightly different than what appears in the Cardi formula. So the point is that on M3 times R, you may want to impose that your supercharges are time independent, so that indeed this is a good chemical potential. And for that, you need to make a little twist, which is also common which is also the case in all the other compactifications in this family. And the twist just amounts to redefining the dimension by the R charge in the theory. So I'm not explaining that in very much detail. It's not going to be very important. But this is a formula that one can keep in mind. That this partition function has an interpretation as just counting operators in flat space.
This part is only, this statement is only conformal.
Yeah, this is for conformal filters, SCFTs. Okay.
Why
So
is the U1 R get broken? Well, basically, if you look at non-conformal, U1 R is broken to some discrete subgroup. If you don't have any of those,
this discussion, when I told you that you can preserve supersymmetry on these spaces, and that there is this nice superalgebra, and you can promote and you can make the R a circle, all of this is only true if there is a continuous R symmetry. If there is no continuous R symmetry, it's no longer true that any Seifert manifold works. There is another restriction which removes many interesting manifolds. But so this is only true if there is a continuous R symmetry. So there is this combinatorial interpretation, and now I can just quote the central thing that I would like to explain. So you can ask, what is the small beta limit of this object? This is the sum of all the operators in flat space with alternating signs and with an exponent that is very similar to what appears in the Cardi formula. So it turns out that when beta goes to 0, it's basically up to some coefficients that I will fix. It's basically controlled by A minus C, where A and C are the central charges that we've seen today in the morning, over beta. Okay, so it's very, very similar to the Cardi formula. And in fact, it's very interesting that when A minus C changes sign, we know of examples of quantum filters with both signs of A minus C. And you see that the behavior at large beta is dramatically different in the two cases. When A minus C has one sign, then it exponentially grows the number of operators of large dimension. And with the other sign, there is exponential suppression of operators of high dimension because of the alternating sign. And this is, if maybe some of you are familiar with what's called Kutasov-Seiberg theorem in the context of world-sheet string theory, it's actually somewhat reminiscent of that. But it's a very different story, so I won't go into that. Okay, so this is the central result that I want to explain. And this is the machinery that we're using. So, how do we see that this is true? Yes?
What is the capital Ri?
This is the R charge. So this is the dimension. This is the dimension of the given operator, and this is the R charge. Okay.
So this limit is also interpolation to 3D.
Yes, so this is what I'm going to use. In this limit, you can think about the theory as. Now, let me just mention that in 2 dimensions, Cardi's formula, the formula that I mentioned in the beginning, is derived by using modular invariance. So the fact that there is an analog of that in higher dimensional CFTs, SCFTs, may suggest that there is something of this sort going on, but it hasn't been understood.
Is this result true again only for conformal theories or also?
Actually, there is a generalization also for non-conformal theories, but in the way I stated it, where there is A minus C, it's just for conformal theories.
Suppose you take a theory that's a deformation of a conformal theory.
Yeah, then this gets replaced by the trace of the R symmetry. But I'm not giving the most general sort of result. Okay, so let me explain how this is derived. So the main tool, this is some kind of high temperature limit. When beta goes to 0, the temperature is effectively very large. So so this is the tool that I'm going to use is the high temperature expansion of quantum field theory. So let me remind you about the high temperature expansion in quantum field theory. There is in fact one puzzle that is extremely interesting that still stands out in this field, and it's very crucial to understand that puzzle for that issue. So the high temperature expansion, so suppose we have a quantum field theory that is heated to some temperature T, and suppose that the temperature is much larger than any other scale. So we studied quantum field theory with temperatures which are much larger than any other scale. In that limit, the theory can be analyzed by dimensionally reducing it to 3 dimensions. So the reason is that how do we introduce temperature in quantum field theory? We take R4, we replace it by R3 times S1, and the radius of S1 is beta, where beta is 1 over the temperature. Okay, so when the temperature becomes very large, one can study the theory by dimensionally reducing it over the circle, and then you have some 3-dimensional effective theory. So let's assume that the theory has a U1 symmetry. So I'm again studying the class of theories that have some U1 symmetry. Here there is no supersymmetry. This is just a general comment about the high temperature expansion. So we take theories which have a U1 symmetry. So we have a conserved current in 4 dimensions. We have a conserved current in 4 dimensions. And as I said, it's natural to introduce a background vector field . It's natural to introduce a background vector field which we can call A mu. Okay, and so suppose you want to study correlation functions at high temperature. The way to do that is to compute the 3-dimensional effective theory for this background vector field A mu. So
my understanding is that if you introduce temperature, even the mass ratio becomes massive.
Yes,
I don't know whether it's case or.
Yeah. So okay, this is what I wanted to say. So if you want to study correlation functions of operators in the theory, such as J mu at very high temperature, you have to. So suppose you want to study them at 0 frequency. So there is no dependence on the S1. This is captured by some effective field theory in 3 dimensions because we're studying stuff that doesn't depend on the S1. Now, this effective field theory in 3 dimensions for the A mu should be local. This is the key. So the theory on R3 is local. Why is it local? Because in thermal field theory, everything gets a mass. Okay, we don't expect, unless we're tuning the parameters to sit at some second order phase transition point, we don't expect massless particles in general. So the theory on R3 is local because when the temperature is very large, all the particles have a mass which is of order beta, of order 1 over beta, sorry, of order the temperature. And so the theory on R3 should be just a local generating functional for the background field A mu, because there are no massless particles, so it's just a local functional. So the theory in R3 is a local functional of A mu. Okay, and this is the main thrust of the argument. So we can just write down the action in 3 dimensions after we have reduced over this thermal circle. And it starts over in general with some function of A0 and then there will, so it starts over with some function of A0, which does not depend on, this function does not depend on derivatives. So this is the 0 derivative guy. So this, we just make a derivative expansion because the functional is local, so it's natural to make a derivative expansion, and that corresponds to an expansion in 1 over temperature. So at 0 derivatives, we just have a function of A0, where A0, so we decompose A to be A0 over dx4, so maybe we'll call it A4. So we decompose A to be A4 dx4 plus AI dxi, and we assume that everything depends just on the xi coordinates. So there is no dependence on the coordinate x4 over which we reduce. So there is this function of A4, zero derivatives, and there cannot be any function of AI at this point because there is no way to write something that's local and gauge invariant. And then at the order of one derivative, there is the following object. I'll need to explain what it means. So actually at the level of one derivative, there are several terms one can write down, but there is one particular term that is extremely crucial for this discussion, and it's also the most interesting term because it's not clear. Something fundamental about it is unclear. So let me write it down and then I'll explain what it means, what the notation means. So the term that we're discussing is one derivative, and it's a Chern-Simons-like term, and I have to define what little a is in a second. So we write I k over 4 pi. There are several other terms with one derivative. They've been classified in particular in some papers of Shiraz, but this is one particular term that I'll define in a second that stands out as the most interesting one.
And the second one will be two others.
Two others, yes. Let me explain what this notation means. So when we study the reduction of the theory from R4 to R3 on this thermal circle, we've taken this ansatz for the gauge field. So we separate out the components of the gauge field along the S1 from the components along the R3. And actually, one can do the same thing for the metric. So one can take a metric ansatz, which looks like dx4 plus ai dxi squared, and then some three-dimensional metric, which is hij dxi dxj, and you assume that everything depends just on xi. So ai, hij, ai, a4 are only functions of xi. They're not functions of the x4. Okay. So when one reduces when one studies this dimensional reduction, it's natural to do a twisted dimensional reduction. So what does it mean physically? Physically, the fact that x4 is compact with radius beta means that we're coupling the system to a reservoir of temperature T. And this AI means that there is some velocity in the fluid. So it's like, you should think about the quantum field theory at final temperature, it's like some fluid. And this means that there is some velocity. So in particular, at one derivative, there is this mixed Chern-Simons term involving the little a and the capital A. And it's a very interesting guy, because there is a conjecture that this k is fixed by an anomaly. The trace of the U1. So this is a conjecture. Minus 1 over 12 trace U1. Okay. So what I want to do is I will prove this conjecture for all Lagrangian field theories. And then we will use supersymmetry to see that this implies the high temperature behavior of supersymmetric partition functions that I mentioned in the beginning. So there are two steps. One is to understand why this is true, and the other is the applications for supersymmetry. Let me just tell you why this is interesting. What does it mean? So what this means is that if you study the two-point function of a current and the energy momentum tensor, so these are some background fields. This is the background vector field, and this is the background metric. So when you take derivatives with respect to capital A and little a, you generate some two-point function. So you generate some two-point function of the current and the energy momentum tensor. And this is given by k, with some epsilon I, j, k, and then pk. Okay, so this is in momentum. This is what it means, and this is what this implies in momentum space at zero frequency for this thermal 2-point. This is some thermal 2-point function. So the surprising thing is that this guy is completely fixed by an anomaly. fixed by the four-dimensional anomaly. This is very, very mysterious. That anomalies are usually defined as properties of quantum field theory in flat space at zero temperature. And here we see, if this conjecture is true, that at least this transport coefficient is completely fixed by some four-dimensional mixed gauge gravitational anomaly. At least the leading term in the expansion in temperature is completely fixed by this anomaly. And it's actually measurable experimentally. So it would be very nice to prove it. All I've been able to do is to come up with a Lagrangian proof, with a proof for Lagrangian filters. So I'll now explain how one can prove this result for any Lagrangian field theory. That's a big space of theories, but it's not everything. And I don't have a complete non-perturbative proof. There are some attempts in the literature, but they suffer from various difficulties. For example, singular geometries and stuff like that. So let me just explain why this transport coefficient should be fixed by an anomaly, and then we'll discuss the supersymmetrization thing. Are there any questions? Okay. Is the statement of the conjecture clear? Or anybody? So what we want to understand is why there is some two-point function in thermal field theory that's completely fixed by a four-dimensional anomaly, and the way it appears in this generating functional is as a Chern-Simon star. So first of all, it's actually useful to start with an example, to check that this is true in an example. So let's start with an example, which is the simplest conformal field theory in 4 dimensions that has an interesting anomaly, which is a massless fermion. So let's start with an example to see if this conjecture holds water. So we start from a free wild fermion. So we're going to do a little bit of thermal field theory for free wild fermions. And we'll see that this conjecture is true. Now I want to mention something that would connect with what I said in the beginning. Notice that in the beginning of this lecture, I mentioned that there are some interesting Chern-Simons contact terms in three-dimensional quantum field theories, but they don't make sense absolutely. They only make sense modulo 1. And here we see a conjecture that somehow wants to go beyond that. It really tells you what's the absolute value of this Chern-Simons term, not just modulo 1. So how is that consistent? This is in connection with what I said in the beginning. So the resolution is that this Chern-Simons field theory or contact term does not arise from a three-dimensional problem. It arises from a four-dimensional problem. Some 4-dimensional quantum field theory coupled to a thermal bus in 4 dimensions. So the allowed space of counter terms is different. And the counter term that we discussed in the beginning of just adding this with an integer coefficient does not exist. It cannot be uplifted to 4 dimensions. So this is why this conjecture is not crazy. Even though you would expect the Chern-Simons terms only are defined modulo 1, in this particular physical application, they are defined absolutely, not just modulo 1, because the theory really is 4-dimensional. That's one comment. Another comment is that this is an integer. Trace U1 is an integer. And you notice that the normalization is 1/12. So this thing is not even correctly quantized. This would be crazy in 3-dimensional quantum field theories because it would mean that you violated gauge invariance. But because we've somehow descended from a 4-dimensional quantum field theory that has an anomaly, it seems that this violation of gauge invariance is legal, which is curious. So free wild fermion. We take a wild fermion on S3 times R3 times S1 with anti-periodic boundary conditions. So this really thermal field theory. So what does it do? So when we reduce this thing on the S1, so we take one fermion in 4 dimensions on an anti-periodic circle, and we reduce it to 3 dimensions. So in 3 dimensions, there are infinitely many quantum fields with masses a half, 3 halves, 5 halves, and their corresponding -1/2, -3 halves. It's all in units of 1/beta. So it's all in units of 1/beta. Okay? So this is what I promised you before, that when you take a thermal field theory, you reduce it on a circle, you get the gapped spectrum. This is why there is a local action at 0 momentum. Okay, so this is the spectrum of a free wild fermion with anti-periodic boundary conditions when you reduce it to 3 dimensions. And now we just need to calculate this Chern-Simons term. So how do we calculate Chern-Simons terms? We calculate diagrams where there is a, little a, and then there is a one loop. Because this theory is free, it's completely saturated by one loop computations. And this loop is going to be proportional to the charge at this vertex and the charge at this vertex. Okay, so we just need to do, and then there's some universal kinematical factor that doesn't depend on anything. It's 1 over 8 pi in some convention. So one gets 1 over 8 pi just from this loop times the charge here and the charge here. So we can call it the charge at A, under A, and the charge under little a. And we need to sum over n, because we have infinitely many quantum fields in 3 dimensions. So we just need to determine the charges. That's easy, because our free wild fermion started its life as a 4-dimensional field with charge 1 under the U1 symmetry capital A. So the charge under capital A is always 1. Okay, so 1, 1, 1. The charge under little a is a little bit more confusing. Little a is this component in the metric. From the 3-dimensional point of view, it becomes like a gauge field because it has a vector index. And the charge of any particle that you get by dimensionally reducing is basically proportional to the momentum along the S1. So the charge is basically going to be the mass, because particles with a high mass come from reducing some mode on the S1 with a high momentum. So it's going to be proportional to that, and so it's 1 1/2, 1 3/2, 5 halves, and so on. Minus a half, minus 3 halves. Is that clear? So these are the charges under capital A, little a. So this sum becomes just 1 over 8 pi. Then there is the sign of n. And then there is the product of this thing. So it's n plus a half. And this goes from minus infinity to plus infinity. So this is the sum over all these diagrams. The normalization is 1 over 8 pi. You should believe me that this is the right answer. And then there is this infinite sum. So we're talking about the sum. We're talking about the sum minus 3 halves times minus 1, because the sign of minus 3 halves is negative. Then we have minus a half times minus 1, plus a half, plus 3 halves, and this goes infinitely far away in both directions. So we actually get 2 times the sum a half, plus 3 halves, plus 5 halves. Okay, so this is the infinite sum that we get. We can divide by 2, and we get 1 plus 3 plus 5. And this thing is 1 over 6. Minus 1 over 6. Oh, with a plus, actually. I think it's with a plus 1 over 6, if I remember correctly. And in the end of the day, this comes out to be 1 over 48 pi. Just following from this. Okay, so this is perfectly consistent with the 1 over 12. Because we get 1 over 12 times 1 over 4 pi, which is the usual normalization of Chern-Simons terms. We get 1 over 48. So this formula is true for a free wild fermion. It's just a simple computation in interval field theory. And from that, it follows that it's true for every Lagrangian field theory. And this argument is like an anomaly matching in 3 dimensions, actually. How much time was it? Because we're blinded by this. Okay, so now let me summarize, and then I'll try to explain why this follows. That this conjecture is true for every Lagrangian field theory. So I'll just summarize what I've said so far. So the summary is that if you look at the 2-point function of Ji with the energy momentum tensor at 0 frequency, let me just write it in detail. So we've been studying the 2-point function of Ji at 0 frequency and some momentum k, and then the energy momentum tensor at 0 frequency and some momentum minus k. then the argument was that this is actually proportional to the trace anomaly of the U1 with some coefficient which was like, maybe in this convention it would be 24 pi, 1/24, okay? So this is the conjecture. This is reflected by a Chern-Simons term in 3 dimensions. It carries the same information as this 2-point function, just the generating function of with some coefficient kappa over 4 pi, and the conjecture is that kappa is -1/12 trace of U1. Okay, so this is the content of what I've said so far. It carries the same information, the 2 equations. Now we've verified that for free fermion. I just now verified it for the free fermion. So from that it follows that it's actually true for every Lagrangian field theory. Let me explain why. What's a Lagrangian field theory? You write some Lagrangian somewhere. If there is a Lagrangian, it means that you can change the coupling constants continuously so that at some point it becomes free field theory. That's the definition of a Lagrangian. When people say that something is a Lagrangian field theory, it's tantamount to saying that there is a way to change the coupling constant so that at some other point in the space of theories, it's continuously connected to a free field theory. Okay? So a Lagrangian field theory is the same as a theory that is continuously connected to a free field theory by changing the coupling constants. Unlike, for example, the 2,0 theory in 6 dimensions, which is not believed to be continuously connected to a free field theory. So suppose you are given some Lagrangian field theory, and you want to check this conjecture. And there is no way you would compute it explicitly because this is some complicated 2-point function in thermal field theory for a strongly interacting quantum field theory. But using this Chern-Simons representation, we can say much more. So from the Chern-Simons representation of this 2-point function, it follows that the coefficient kappa is independent of coupling constants. Okay, this is a very strong result. It says if you compute this 2-point function in 3 loops, 7 loops, doesn't matter. It would not depend. It would be saturated at 1 loop. So any loop order contribution to this 2-point function other than 1 loop must be trivial. How do you prove that? It's just a 1-line argument. Suppose this coefficient dependent on the coupling constants. Then you could have imagined that the coupling constants are not quite constants, but they are functions in space. You just promote the coupling constants to functions. Then this would not be gauge invariant. And then you're done. This is quite a common argument in quantum field theory that one can use in many different contexts. It sounds like a sleek argument, but it's actually correct. So it establishes a very strong result that kappa is independent of coupling constants. And therefore, it's the same here as here. And here we just verify that it's correct. And since it's correct in free field theory, and since the anomalies don't depend on coupling constants too, then it must also be correct here. Since both sides don't depend on coupling constants, and we check that it's true in free field theory, this relation, if it's true in free field theory, must be true in every theory that's continuously connected to free field theory. Yes?
So if I view this as a Hopf anomaly matching condition.
Yeah, it's like Hopf anomaly matching in 3 dimensions.
Yeah, but I mean from 4 dimension down, 4 dimension could also be interacting. And I mean then wouldn't that automatically be independent of coupling constant because the anomaly matching is independent?
Yes. So there are several ingredients here. One is that I've proven that this is independent of coupling constants. What's the argument? The argument is what I said. If it did depend on coupling constants, and if you thought about the coupling constants not as constants but as functions, this would not be gauge invariant, and therefore there would be a contradiction. Okay, this is step 1. Step 2 is that the right-hand side of this equation, of this conjecture, is an anomaly, which we know from 4-dimensional physics by the 'Hopf argument is independent of coupling constants. Therefore, both sides are independent of the coupling constants. So this conjecture makes sense. That's all I'm saying in so many words. For this conjecture to make sense, this has to be independent of the coupling constants. This is clear from this presentation. And therefore, if it's true in free field theory, it's true in every Lagrangian field theory. And indeed, some papers by Demson and